Welcome to Tarragona from CellSpex. Today I'm going to show you how to set up a linear combination of model spectra fit. As part of this demonstration, I'll show you how to extract your model spectra and how to manipulate the results. So I'm going to be using the data in this file, which is in your examples directory. So this is in Program Files, CellSpex, Tarragona Examples, and it's called 01 LCMS cytochromc.tdf. And this is the final file. So the first thing I'm going to do is remove all the work I've done now so that I can show you how I did it. So for data contents, I'm going to remove all of these, and I'm going to remove the fitting. And these are the spectra, model spectra that I've extracted. So I'm going to start by viewing the spectra. And before I collected these spectra, I'd already intensely calibrated my system. There's a separate video on that. So one thing I have already is that I've extracted the attenuation at 550 nanometers. So this gives me a temporal profile of my experiment. And I'm animating this graph. Cytochrome-C comes in two forms, the oxidized form and the reduced form. And the reduced form has a strong peak at 550 nanometers, which is why I chose to extract the attenuation at 550 nanometers. So if you go to the beginning of the experiment, and there's no signal here because I just have buffer in the system. At this point I added 10 micromolar of cytochrome-C from sigma, and you can see the spectra changes, and it's mainly in the oxidized form, but you can see a small peak at 550 here. Over a period of time you can see that peak grow, and then I gave 50 micromolar of ferricyanide, and that oxidizes cytochrome-C. So this should be this oxidized form, and then at this time period here I gave 1 millimolar of ascorbate, and that reduces the cytochrome-C, so this is now the reduced form. So you can see that the oxidized form and the reduced form are different. So first of all I need to extract the two basis spectra, so I'm going to put a double cursor on, and I'm going to choose this epoch for my oxidized. So I should go spectra, average, attenuation, and take my average, copy it, close, and paste it into this graph. And then I'm going to take an epoch for my reduced form, and it's finished reducing here. So I'll take that epoch, spectra, average, attenuation, and now I'll copy that, and that's reduced form. And I'm going to make this blue for reduced. So these are the two forms, but this is in sort of arbitrary units. I added 10 micromolar of cytochrome-C, but this is a nominal amount. But one of the things I know is that the peak of the reduced form should have an optical density of 27.7 OD per millimolar per centimeter. So that's there. And I've actually got a value of 0.2 at the moment. Let's just find the top. So I'm going to put types 3 to find the real top. So that's fitted a quadratic through 3 points each side. So this is the top. So that's 0.201. So I need to normalize these spectra. And to do that I'll use the calculator. So view calculator. And I have two constants, 0.201, which is the current peak, and 27.7, which is the calibrated one. So I'll start with the reduced. I click on the reduced, it appears in the calculator. I'm going to divide by the first one to normalize it, and then multiply by the second one to give me my calibrated spectra. And now I'm going to change the units. So wavelength, this is going to be site C reduced, and this is in specific absorption, OD and millimolar per centimeter. And then I'll click on this graph and export it, and I'm going to make it blue. And I do the same thing with the oxidized spectrum. So normalize it, divide by this one, equals, and then multiply by the quantity, equals, and change the unit. So this is cytochrome-C reduced, oxidized. And this again is specific absorption. And if you don't have the unit you need, you can click on the new one button to create a new measurement. So I'll click OK on that, click on this graph, and export it into that graph. So now I have my two spectra, and now this is the time to add some notes. So the name is site C reduced, and I have the notes in the clipboard to make it a bit quicker. Reduced equine cytochrome-C, measured day, oxidized by ferricyanide, reduced by ascorbate, and my buffer. And I need to do the same for the oxidized. Copy that in, and this should be oxidized. And then I'm going to name this site C oxidized. Okay. So now we can set up the fitting. So I'm going to set up each one separately, each spectrum separately. So I'm going to copy that spectrum, fit in new, create a new linear combination model spectra, fitting and edit it, and then in the new component I'll paste the component in. And now I'll get my oxidized one. Copy that one, fitting, LCMS, paste. So the y-axis here is in OD in millimolar per centimetre, but my concentrations will be in micromolar. So to make my life a little bit easier, I'm going to change this to OD and micromolar per centimetre. So I need to create a new unit, OD micromolar centimetre, and one of these is equivalent to 1000 OD a millimolar per centimetre. Okay, and so now it's in micromolar centimetre and my values will be in micromolar, and I need to do that for the reduced as well. Change the unit to there. Okay, I have a path length of 1, no background, and that's all I need. So now I'll click OK. I'll remove the spectra and view the fitting. So I look at the data, the fit and the residual. And so now as I bring my cursor around, you can see my fit, and I have a very good fit. Not so good there. So let's go ahead with this and see what we get. So if I look here and go to the fitting, I have 7.28 micromolar reduced cytochrome-C and 0.07 micromolar of oxidized cytochrome-C. So I need to put those into the data items. So I go fitting, parameters, I need that one, reduced cytochrome-C, and this is in concentration and it's going to be in micromolar. And I need the oxidized as well, and this is also in concentration in micromolar, because my spectra are in OD and micromolar per centimetre. Okay, and then I can fit those spectra. Well, let me show this first. Do view data, time, double click to put them in, and go fitting, start. Fitting, start. There we go, and that's my fit. So one thing I'll do now is I'll just get the total as well. So data, contents, I'll create a new one, site C total. I'll make that purple, it's in concentration of micromolar, and I'll create quick mass operation, total, A plus B, reduced and oxidized. And while I'm here, I may as well create this percent oxidized as well. So that's going to be a ratio as a fraction. I'll keep that red for cytochrome-C. Mass, create a new one. Output is the, whoops, that didn't work. It should be a percent oxidized. Percent oxidized. A over A plus B. So A will be the oxidized and B will be the reduced. And so that will give me my percent oxidized. And now I can go data, view, and I can look at the total. And in here, I'm going to put the oxidized, so data, view, the oxidized. And I'm going to clear this data out because this is when I don't have any cytochrome-C. So when you don't have any cytochrome-C, you can't have an oxidation state. So I'll start it here. So data clear, and then I can rescale that. So now I can see what's happening in my experiment. It goes in, and I have about 7 micromolar of cytochrome-C, and it starts to reduce. And then I add the ferricyanide. Let me put the events on. I add the ferricyanide to oxidize it, and then I add the ascorbate to reduce it, and it becomes fully reduced. And as I come up here, I now see there's a drift on my signal and I'm no longer fitting properly. So what I will do is add an offset to my fitting. So fitting, LCMS, and I'll add an offset. And now, when I move the cursor, now I'm getting a very good fit. As I come over to here where the fit wasn't so good either, now again I've got really flat residuals. So there must have been an offset appearing in my signal over time. Okay, so I'll take that and I'll do that fit. So now if we take a look at the total of cytochrome C, so we'll just zoom up on the very top of this, you can see my total isn't perfectly flat and there's a little bit drift, and here my reduced is slightly greater than my total, and that means that my oxidizer has gone negative, very slightly negative. In terms of the oxidation state, I'm getting -1% oxidized or so. Where are we? -0.5%. So this isn't perfect data, and that's because there was a drift during my experiment. So what I need to do is now work out what that drift was and fix it, and then repeat this. So that's the end of my demonstration. Thank you very much.